Hello there. This is James from AccelerEyes. I think we're ready to begin. Sorry for the delay there. We had to reinstall the driver last minute on the NVIDIA card. So I'll just dive right in. So this is going to be about a little less than 30 minutes presentation about ArrayFire, and we'll go through some examples. We'll show some basic code, how to get set up. We'll be using Visual Studio Express, I think, 2010. And so let's just go ahead. Again, my name is James. There's a chat window if you want to ask any of my colleagues the questions. They'll be answering concurrently while I'm going through the presentation. So AccelerEyes puts together, just kind of a quick overview, AccelerEyes puts together two main products, ArrayFire and Jacket. ArrayFire is for C, C++, Fortran, Python. It works on CUDA as well as an OpenCL version. It's been out since about 2010, and it's currently in version 1.2 with CUDA 4.2. And then Jacket, which will not be the focus of the webinar, Jacket is for MATLAB. And you can compare it to like MATLAB's own PCT. There's the URL down below. It also runs on CUDA and OpenCL, and it's been out since about 2007. So over the years, we've accumulated lots of customer success stories. There's several thousands of paying customers, and many multiples out of free customers. People have done trials, and so we've gotten a lot of great feedback of speed ups on the GPUs with very little coding involved. So we'll go through some of that examples, but basically it's being used in almost every, at this point, almost every industry. Most major engineering, finance, and biotech kind of companies have been using ArrayFire and Jacket. So let's jump into a first example of ArrayFire so you can just right from the start see what it is. Here's kind of a classic example of estimating pi using kind of a Monte Carlo approach. So to start out, this is regular like C or actually C++. You include the header file, open the namespace, and then we start by throwing down a bunch of random points on the unit square. So in this case, 20 million points spread over 0 to 1. And then we count how many fell inside the unit circle. So we sum up using a floating point sum. We sum up the number where the distance from the origin is less than 1. And then since we're only doing the upper right quadrant, from 0 to 1, we multiply it by 4 to get all the quadrants and divide by the number of samples we threw down to see what percentage, what fraction fell inside the unit circle. And we print it. So that's kind of the basic idea. All of this expression here and the sum is happening on the GPU, but then it pulls it back from the CPU of type float and does this simple like multiplication by 4 and a division by n. All that's done back on the CPU. Printing on the CPU. Moving along, while there's the basic array container object, there's many different data types that can sit underneath it. For instance, a single precision floating point, 32-bit IEEE data, 64-bit doubles, unsigned integers, signed integers, booleans, which are typically stored as 8 bits, just have either 0 or non-zero status, as well as complex data types. And you can create, here's examples of creating uniform data, or as well as random integers where every bit is random. The arrays can be vectors. Here's like a row vector. They can be matrices, volumes, or n dimensions. You can do subscripting to pull out single elements or a row, and just different slices. There's kind of these keywords like end and span, which can help you pull out and reference things a little easier. So here's an example of pulling out this slice of the volume. It's the second slice. It's 0 index. That'd be like actually the third slice, sorry. Here's some examples of how you can generate values in arrays. A matrix of 0, or in this case, a column of zeros, a matrix of 1s, random identity matrix. You can do complex values. The last argument can optionally be the value. or the data type, that by default is 32-bit float. You can also take host data, CPU data, like an array, and push it out to the GPU. Keep in mind that it uses Fortran storage order, the same as BLAS and LAPAC. For arithmetic, you can do expressions. Here's some simple element-wise expressions. And this bottom one, are rescaling every complex value by to the unit circle, to be a unit vector. Here's some examples of calculating the L2 norm of every column of a matrix. And the last one is every row. So by default, sum will do the 0 dimension, the first non-singleton dimension. But you can also, this green here shows how you can specify different dimensions to do a summation along. Here's some subscripting examples where you can grab, for instance, the second row or the last row, the end row, or grab everything except the first column. You can grab a sequence of elements or skipping at some skip. So for example, here's from the first element, the 0 element, all the way to the end, and skipping every 2 elements. So you can see 0, we skip 1. A lot of these examples are on the website. Go to AccelerEyes.com/ArrayFire. That's where we have you can get support, and we have a lot of the documentation for ArrayFire. Some more examples of subscripting and assigning values, copying this vector, this row, into the first row of this matrix. You can also start doing linear algebra. Here's LU factorization or LU decomposition, solving a linear system, AX equals B. There's interfaces for Python, Fortran, C, C++. A lot of them, the Python one, for example, follows much the same API as NumPy from SciPy. For Fortran, you can create an array data structure, an object, and then do arithmetic on that, FFT, signal processing. One of the most interesting things about ArrayFire are the visualizations it enables. You can do these kind of scatter plots in different colors, visualize a 2D image, look at signals or surface plots. Here's another scatter plot. Here's a mesh, colored surface, various different things. So I'll go over and talk a little bit about how that works. So it lets you, while you're doing computation, it lets you do rendering asynchronously. You can, in a loop, here's a loop where you can infinitely loop, create a random matrix, and plot it as a 3D surface over and over again. So if you ran this program, you'd see this just flickering here as a random surface is generated, in this case, color, obviously. Now, when it hits this plot command, it'll go ahead and queue this up for render, but it'll continue doing your computation. It prioritizes computation, and unless you ask it to block, which there's a command where you can wait for it to finish drawing. By default, it'll just queue that up and keep on doing the computation. It throttles visualization at about 25 or 30 frames per second. So there's several different commands you can use to do surfaces or lines, images, vector fields, point clouds, volumes. We can do density, and as well as colored images. Change you can do subfigures. You can change the color palette, change the title of your figure. So another very interesting thing about GPU computing is it enables data parallel for loops. Now, what does that mean? Here's how you might program matrix multiplication. How in a for loop you take this slice of a volume and multiply it against this matrix, store it into this slice of output volume. This is a standard C for loop. So here it does the first iteration, this vector against the matrix, store here, and it does the second iteration and the third iteration, all serially done one after the other, 3 entire kernel launches. G4 is, so that may work fine if you have one huge matrix that you need to do, but if you have a lot of small matrices, it's not well suited for the GPU. So what G4 is good for a lot of small problems. So instead of doing that serial matrix multiplication, you can switch it out to be a G4 loop. Here we'll do 3 tiles. All the loop body looks the same as the for loop. But in this case, this happens in one kernel launch. Let's go back to the matrix multiply. Changing just the for loop construct, it does all 3 iterations simultaneously. Lets the hardware do the scheduling. So you can think of that as kind of a grid. It's vectorizing the entire operation and just executing almost like one big volume. Another thing that ArrayFire makes easy is multi-GPU computation. Here's a trivial example where you are using device set to change to GPU 0, 1, 2, all the way up to n-1, generating random values on that GPU, computing the FFT, and moving on. So none of this is blocking. It'll go ahead and change device and keep on going, queuing up work in the background. Your host side loop will keep running, and then all GPUs will be computing simultaneously. Included in ArrayFire are hundreds of functions, everything from data analysis like reductions, manipulating vectors and columns and rows, statistics, convolutions, FFTs, signal processing, interpolation, rescaling, integer and floating point sorting, indexed sorting, lots of image processing we've been working on the last few weeks of revamping a lot of these functions, extending performance and cleaning up the interface. Also a lot of linear algebra to do SVD or LU, compute eigenvalues, solve systems, matrix factorization, and hundreds of more. Speed. Let's talk about speed. So here we do some quick benchmarks, plotting gigaflops. So the higher the trend line, the better. And all these ArrayFire is blue. And we compare it to a lot of the CPU libraries, like Intel's mass kernel library, MKL, Eigen, Intel's performance primitive, and Armadillo. You can see the GPU achieves much higher gigaflop performance doing matrix multiply or vector sum. Here's convolution, vector convolution over here, as well as square signal convolution, 2D convolution. And all these were comparing the state-of-the-art Intel performance primitives, and ArrayFire wins. Doing a cumulative sum or accumulated sum, the sorting achieves state-of-the-art throughput. One of the things we really strive to provide with ArrayFire is a simple interface that doesn't change and lets you migrate from one hardware generation to the other. Each release, we work on improving the code behind the scenes, and with every new architecture that comes out, we tweak and tune it, and your code, you upgrade our library, and your code will automatically run on Tesla, Fermi, Kepler. Behind the scenes, we work to run thousands, tens of thousands of unit tests and push performance. One of the best things about ArrayFire is that it's free. For single GPU, you connect to our internet license server, you get the full performance. There's also a pay version, professional version, where you can get multi-GPU, you can get phone support, linear algebra, you can run it offline. So one of the things that with a lot of libraries you have to think about is the build versus buy decision. So you can spend your own time porting your code, maintaining the code, documenting routines, developing and testing, or you can use ArrayFire and leverage a lot of software libraries out there where we take care of ensuring rigorous testing and improving our documentation and maintaining our code with each generation. So it reduces a lot of your time to market, it reduces the costs that you incur, and helps you just prototype faster in a higher level interface. Two other things that ArrayFire provides, or AccelerEyes provides, are custom development. We spend a good portion of our time working with customers, individually porting their CPU code, rewriting critical sections, extending existing projects. And we have years of experience in numerical and image and signal processing, linear algebra. We do also training courses, typically 1 to 4 days, and either on CUDA or OpenCL. We provide hands-on, part of that hands-on work with your code. So just to kind of recap, check out ArrayFire. There's the URL. There's also Jacket if you're interested more in MATLAB computation. You can check out the comparison page there where it just clobbers MATLAB's own PCT. And that's it. Now let's go through a Q&A. So we have a question here from David. How does it compare to Thrust? Thrust is a T-H-R-U-S-T. Thrust is a library that is built by NVIDIA engineers. It's kind of open source, like and it provides a lot of the computational primitives. I would say that Thrust is more geared towards people who are already computer scientists, who are used to using template programming, who are not afraid to write CUDA code, but want some of the standard algorithms kind of packaged and wrapped up for them. So, it's a lot more verbose. You definitely, so here I have the Hello World example up. There's nothing in Thrust where you can grab a last row of an array, or you have to use QFFT, a whole other library to FFTs. Element-wise arithmetic is a lot more complicated than simple expressions like this. So when you're using Thrust, it tends to obscure the actual algorithm because you're using kind of a verbose syntax. In addition to that, we do a lot of benchmarking against it, and ArrayFire typically beats, it performs as well or better than Thrust. We do use Thrust in some pieces of ArrayFire where we found Thrust to perform very well. And so we just had another question here. Let me hop over. Another question. Says Jacket OpenCL, is it for the student community for personal use? The OpenCL version of Jacket you can use for student use. It's free. It connects to our license server. That's no problem. For Jacket, there's academic pricing, which is about, I think it's about $350 US, and so it should be reasonable for kind of academic use there. Sparse matrix support, that will be in ArrayFire Pro. There's limited support right now. It's on the roadmap for the next few months to build that out with solvers. Right now you can construct sparse matrices. You can do multiplication, find non-zero elements. Okay, let's. If there's any more questions, actually, it's best instead of directing your question to me, the presenter, to direct your question towards the panelists. Okay. So, hello world. So in this case, we have, as before you saw, including the ArrayFire header file, open the namespace. It's good to practice to have everything in a try-catch loop. Generate random uniform matrix. Here's do some simple element-wise arithmetic. Compute the FFT. Grab the last row. So you can look through this on your own. This comes with the ArrayFire installer. You can pull the data back to the CPU, get a pointer to it back on the CPU. When you're done with it, free it. And you may want to catch the exceptions because there might be invalid syntax at runtime or other problems that may arise. So we've got that. Let's set it to be release, 64-bit. Click go. Pops up a console window here. It's loading up all the NVIDIA libraries, connecting to our license server, printing out information on our GPU. Here we can see that it's using the 4.2 toolkit on the system. The driver is one of the latest ones. Scroll back up there for you. Version 3.05. I should point out here that there was a significant bug with the NVIDIA driver prior to version 3.04, where there would be a significant startup delay when it loads the CUDA toolkit and all the libraries in ArrayFire. So if you're going to do ArrayFire or even Jacket development, you're going to want to upgrade to drivers 304, 304, or higher. The display device is a Quadro, and it shows me that there's about 4 gigabytes free. So here you can see the results of all those computations. You can see complex values being printed after the FFT, grabbing the last row here, you can see, and zeroing out columns. And it's waiting for me down here at the bottom to hit enter. There we go. Let's run another example. The vortex example. This is a spinning vortex where particles drift towards the bottom. So this is standard CPU code to kind of set some parameters, generate a bunch of particles, uniform grid. There's also a lot of the platform independent constants like pi, infinity, NaN, not a number, which are available directly in ArrayFire. This is the basic equation we're going to be running as things spiral around the center and fall towards the bottom. Set some timers so we can print out iterations per second at the bottom. And here's our main loop. It goes until a total, or elapsed seconds, which I guess somewhere, runs a total of 10 seconds. And continually moves everything down and keeps on plotting. If it's not running in console mode, it plots the XYZ points. So let's run that in the background here. So it's going to run the simulation. It's loading up the NVIDIA toolkit and driver, initializing everything, setting up the graphics. Here we go. Keep in mind this is kind of an old Quadro, but you can see everything kind of drifting and falling to the bottom. There we go. Let's run that one more time. I'm going to do a longer run of 30 seconds because in this case it's an old computer. There's a timing delay, so I rebuilt it. It's going to run it. It's going to set up the figure and everything. Typically, your programs will be longer running, so you won't really notice the startup delay here. And there we go. Meanwhile, it's putting in progress. How many iterations per second? Newer cards will probably have much higher frame rates here. go ahead and fill that. Another example here. Image processing. Look, we have routine example code to kind of load an image, convert to different color space, compute histograms and equalize based on histogram, split out the RG and V channels, do morphology, for instance, closing operation, compute how many connected 8-point regions there are, compute the area of each region, and we're going to show that all on the screen. So let's switch to release mode, 64-bit, build it. So this, we're going to use the subfigure plots. We're going to create a window of this size. We're going to show several subfigures, about 12 of them total with different things. We're going to plot color, transpose the image. There we go. Here we did transposing. We resize to a fraction, a third, downsample to a third of the image, rotating it, smoothing it, dilating, pulling out all the edges, doing the morphology and close operation. So you kind of fill in a lot of little pockets. Here you can see the kind of connected components, figuring out the regions, changing the hue, pulling out just the blue channel, histogram equalization. So I think that's it. We have a couple other examples that I recommend. The starting place to go is if you go to AccelerEyes.com. ArrayFire here is the second column. Click on Learn More. Here you can kind of see we've done a lot of benchmarks. One of the good, you can go ahead and download it and get going. You can click on this documentation here for C, C++. And this is a good place to get started, learn a little bit about the library, see the Pi example we went over, and I'll show you the steps to getting up and running here. The Getting Started page will show you how to, on different operating systems, how to use licensing and get going, and examples of what it should look like on your end. Quick reference is also a really good thing to go through, and you kind of get a quick survey of a lot of the different functionality that's available. And that's it. Thank you for your time. Oh, one more question, I think, here. One last question. Do you expect sparse matrix support to be more fully developed in the next few months? Yes. So we're already, we've been making arrangements to work with a third party to get iterative solvers. And with that, that'll open up a lot for the sparse matrix support. So if you send an email to sales@AccelerEyes, we can, with any kind of specific functionality or features you want, we can make sure to notify you when those roll out into production. Sales@AccelerEyes. Another one is, are all these examples packaged with ArrayFire? Are all these examples packaged with ArrayFire? Yes. You can actually even see them online. So if you click on, if you go to the ArrayFire/C, AccelerEyes.com, ArrayFire, click on examples here. And there you can just browse all the examples directly. Is there a way, another question is there any way to use ArrayFire to accelerate operations on string data in Python arrays? The answer is not quite. You can do manipulate integers. The GPU hardware is more well suited for either 32 or 64-bit data. So if you're talking about character strings, it doesn't map well onto little multiprocessors. But if you send us a code sample of kind of what you're aiming to work with, we might be able to show you how that maps onto the GPUs. So there again, if you can send an email to probably support@AccelerEyes, support@AccelerEyes.com, with some example of what, or some description of what you want to do, we can point you in the right direction probably. Okay, that's it. Thank you for your time.